Similarity alone misses the links between entities, documents, and evidence. I will combine vector retrieval with relationship expansion in Neo4j using Python to make search more connected. This is the pattern you'll be able to implement by the end, which retrieves similar texts using vectors and expands graph links to return connected evidence. I'm Professor Pi, teaching search and IR with simple Python. Many search systems stop at text similarity. They return documents that look like the query, and the job is done. In real workflows, we often need more than similarity. We need why a result matters, how it connects to known entities, and what other documents support it. That's where hybrid graph search helps. Neo4j is a graph database that also supports native vector search. That combination fits tasks where text and relationships both matter. Think question answering over documents that mention people, products, or drugs. Success looks like fast top candidates, plus a small, connected evidence set that justifies a choice. At a high level, the idea is simple. Use vectors to find likely matches for a query. Then expand from those matched documents along relationships to gather related entities and supporting documents. The goal is a ranked set that blends semantic fit with relational evidence. We will build a tiny demo. It seeds a few short documents into Neo4j, links them to entity nodes, runs a vector nearest neighbor query, and then expands to nearby entities and documents to form a hybrid ranking. You do not need deep math. I will show the flow step by step so the code feels predictable. Now, we will create the graph and seed documents. This snippet connects to Neo4j with the official Python driver and seeds a tiny document corpus. The graph database driver call opens a bolt connection and prepares a session for Cypher execution. The session.run function executes a compact create statement that inserts 3 doc nodes, each with short text and a small vector stored under the vec property. Returning a count from Cypher lets the code pull a deterministic integer using single on the result. The variable n holds the number of documents successfully created and becomes the basis for later retrieval steps. The printed count confirms the graph is ready for vector and link-based queries. Next, we will add entities and crosslinks so results can expand into evidence. This code enriches the Neo4j graph with lightweight entity structure and crosslinks. The session.run call first unwinds a few names to merge ent nodes, ensuring entities exist exactly once. It then attaches doc nodes to their entities using merge with the mentions relationship, binding text units to interpretable nodes. A second unwind defines pairs of related entities and merges directional related edges to form short paths. Afterward, a small match computes the total number of related edges stored in the variable m. The printed count verifies the entity backbone that later supports multi-hop evidence expansion. Now we will try a vector nearest neighbor query to find the best seed document. This example performs vector retrieval in Neo4j using its native vector index. The variable q holds a tiny query embedding. The session.run call creates a vector index named docvec over the vec property with cosine similarity and 2 dimensions, enabling fast approximate search. A second session.run invokes db.index.vector.queryNodes with k equals 2, yielding candidate nodes and scores already ordered by similarity. The list of rows is collected for deterministic access, and top stores the best scoring document. If you increase k, you broaden recall, but pay slightly more latency. The printed ID and score confirm the nearest neighbor under the configured similarity. Next, we will expand that top vector match into linked evidence across entities. This snippet grows the top vector match into linked evidence using Neo4j relationships. It first retrieves one seed document with db.index.vector.queryNodes, then matches from that node to its entity via mentions. The second match walks related edges up to hop steps to find neighboring entities and the documents that mention them. The variable row captures the seed ID, the size of the evidence set, and a small list of neighbor IDs. Increasing hops surfaces more distant but noisier support. Decreasing hops yields tighter, higher precision context. The printed evidence count shows how much connected context the seed can marshal for reasoning. Finally, we will combine vectors and evidence counts into a single hybrid score. This code produces a compact hybrid ranker in Neo4j that blends vector and graph signals. It queries the vector index with db.index.vector.queryNodes to get 3 candidates and their similarity scores. From each candidate's entity, an optional match gathers supporting documents via related up to 2 hops, counting distinct helpers. The variables alpha and beta weight the vector score and normalize support count into a final score H, computed in Cypher. Sorting by H returns the best trade-off between semantic match and connected evidence. The printed hybrid score demonstrates how relationship context can move rankings beyond text-only similarity. This toy example maps directly to a real QA or evidence retrieval task by replacing the 3 documents with a larger corpus and a production embedding model. The same pattern scales: vector candidate generation, entity-backed expansion, and a simple weighted blend for final ranking. Recap: what it is: vector first retrieval, followed by graph expansion to collect supporting evidence. When to use it: when you need both semantic relevance and relational justification. One caveat: more hops increase recall, but can introduce noisy, irrelevant links. Next step: scale the pipeline by increasing candidate count and tuning the alpha-beta weights that blend vector score and support count. Then measure precision at 1 and timing. That tuning will show how much relation context helps for your data. If short, practical IR helps, subscribe and watch the IR videos.